Okay, so thank you very much for the introduction, and thank you very much for the invitation for me and for inviting my group as well. It's very nice to be all here in Paris. And okay, I'm also talking about generative modeling, but I have a bit of a different perspective than the ones that were discussed today. I'm interested on these models, in principle, to extract information that I can interpret in certain form from the data, and in particular, I want to use energy-based models for this, and certain kind of energy-based models that I know how to analyze. So I'm a bit fixed with the model. I don't want to approximate the probability in this sense. I want my model, but I would like to train it well so that it reproduces the data as I want. Okay, as I will discuss, if we try not to accelerate the sampling, I mean, we try to train these models using the standard procedure that requires sampling, as it was very nicely explained this morning by Stefan Mala. We get very weird effects that actually they can be explained very easily analytically, and that's what I will describe later. Okay, I will. If I manage to make this work. No, it doesn't work now. What? Yes, I put it and I tried before, but I don't know why now it doesn't work.
Because this is yours, right?
Yes, but
yeah, this one
I checked it before and
yeah,
okay, we try with another. Oh, we do. I just jumped. So I will begin a bit illustrating the kind of things that we think we can do to extract information from data. So I will start with applications in which I should be able to train well the machines. And later I will move to the training of the RVMs, and I will solve the problems that we get when we use non-convergent Monte Carlo sampling. And in 2 weeks, I think Aurélien will talk about the how to optimized algorithms that we can use to try to do the Monte Carlo well. This I'm not going to enter today. Okay, so I'm interested in the generative approach. Okay, I suppose nowadays everybody knows what I'm talking about. So I want to feed my neural network with data. I would like to train the parameters so that my neural network is able to generate new data, hopefully as similar as possible as the original one. Okay, there are many possible methods that do this. I will center on this energy-based model, which is quite, it has quite a common framework with statistical physics. In fact, they were proposed from this field. Okay, most of the data that I will show are images because it's much easier to illustrate the problematics. But normally, for me, what I'm interested in is in other kind of data that is very structured. Typically, it can be genome sequences or protein sequences. But okay, normally it will be just data, just images, and normally the data that we are studying, typically it has inner categories. For instance, I mean, in the MNIST data, it's very clear we can have different images for the same digit, for the 4, or if we have protein sequences, each sequence might have a different biological function, and one would like ideally to assign which is the biological function of different sequences in a protein family. Or for instance, if I have the human genome mutations data, I can know, for instance, which is the origin of the individual I'm studying. For instance, the continent or the race, well, basically the population. Okay, so in principle, if we generate, we could either try to do it completely unsupervisedly. So we just want to generate different numbers, but we can also can generate conditionally. Okay, if I can tell the machine that I want to generate a 2 or I want to generate a 4. So I can generate different numbers with a label. Why I want this? Because as I said, I'm more interested in the sequences. I would like to have a way of generating proteins, for instance, with a given biological function. Okay. So in principle, we want to generate looking at data. We could have labels or not labels or whatever. Okay, so the energy-based model, they have a very easy structure. Okay, we're going to have a data set, for instance, our images, and we want to encode the empirical distribution of the data, the samples that we have, in the Gibbs-Bosman measure of a given model, a given energy model that in principle it could be whatever. Okay, the learning is going to consist in finding the right parameters so that these two distributions are as close as possible. Okay. So if we have well-trained these models, we can do, for instance, Monte Carlo and try to find the typical configurations of this model. So we generate new samples, for instance, new digits. Okay, it's clear that if we train well this kind of models, we not only have the ability to generate data, we have the ability to model data to get an energy function for our complex data entries. So if we have a simple enough energy function, we might be able to learn something about the composition of the data. Could be the building blocks or which variables interact with other ones and all this. So we can try to use these energy functions to model and to interpret data. Okay, so the point is, I said I need a simple energy function so I can analyze it somewhere. Okay, it's an approach that we know quite well from physics because I've been doing with the inverses in problem for a lot of time. So if we want to model data, what we can try to do is to model the statistics of the data. So we can go for the simplest thing. So we want to model the typical frequency of each pixel, the pixel 1, or we can also try to model the correlations, which is the typical probability of finding black here and white here. Okay, so we can try to find the model, the more informative model that reproduce the statistics that I want. Okay, one can quite simply see that the model maximizes the entropy that satisfies this condition and also is normalized is nothing but the easy model. So this is nice because in statistical physics we love the easy model, so fantastic. Okay, so what we want in the learning in this case, it will be, okay, we would like to infer which are the couplings and which are the effective fields based on the data. Okay, why we want to do this? For instance, this has been done for a long time with a lot of success in proteins. Okay, we can have protein families in which we have the sequences of proteins that are linked by evolution. They have been aligned somehow to know which is the position 1 of a given amino acid in different proteins of the same family. So normally there are proteins that in different organisms, they have similar functions, and we can try to study the statistics of this amino acid. So what it's seen is, for instance, I don't know, you can see that if a residue has been conserved all over the evolution, it means that you cannot change this amino acid because otherwise the protein breaks itself, all the folding structure disappears. Because, I mean, in principle, mutations can all happen, but we can only see the individuals that have gotten until here and they didn't die. So if the protein doesn't work, okay, we can see other statistics that are more complicated. That, okay, if I have an R here, I have to have a D here, or in the other way. We can see that there are some sites that they co-evolve together. This tells us that if we cannot do random changes there. If we change one amino acid, we are obliged to change the amino acid in the other way because otherwise the structure is going to break down. Okay, one can see actually that when looking to the actual physical folding structure, that these co-evolving amino acids tend to be in contact in the structure, so that if we mutate too bad, this contact breaks out and the structure disappears. And I don't know, in proteins normally, most of the functions are associated to the three-dimensional structure of the protein. Another typical application of this inference inference problems are the spikes in neural networks. One can try to see when different neurons light to see which neurons are connected to which. Okay, so the typical situation is this. We have data and we try to infer which positions are connected to others. Okay, the problem is that now if I try to do this with the MNIST data, okay, I can infer doing inverses in a coupling matrix, that will be this one, and I can infer the external fields associated to this data. But I said that, okay, I can use these kind of things to interpret, but they have to be generative as well. I should be able to generate new data. Okay, if I try to get which is the typical configurations of these models, I get, okay, it recognizes well that it's black around, but it clearly does not generate now. Okay, so what's the problem? Okay, we were trying to fit the correlations up to second order, but it's clear that we need more correlations to describe the data. So the easy model is somehow not powerful enough to describe at least MNIST data. It's well if we are doing the inversing, we are creating data with this Hamiltonian, but if we want to do it with arbitrary data, it doesn't work. Okay, in principle, we could do exactly the same trick that I will discuss in here, just by saying, okay, let's try to fit now the three-body couplings or the other three-body correlations or the n-body correlations, and we can end up with a model that would have many parameters. The problem of this model is that clearly the number of parameters is diverging so fast, and we are not even sure that we need all these couplings. Normally, I mean, we would reasonably we think, okay, there will be some higher order correlations important, but not all the three-body correlations are going to be important. So this is not very practical. But there is quite a simple solution to this. That is the restricted Boltzmann machine. Okay, the restricted Boltzmann machine is going to be very, very similar to the easy model structure. But now we have two kinds of variables that it could be spins for stress. We have the visible that are going to try to encode the data variables. And we have the hidden variables that are latent variables. They are there to encode the correlation within the pixels, for instance. Okay, and one important thing of this is that we can see that
Amazing.
Okay. Because I didn't introduce this. If maybe this is the problem. No.
Which mic?
This mic is now not working anymore.
Yeah. Okay. But I think it's working here, no? Or at least in myself. Huh?
This one is not working. I mean, and that's why Grant seems quite sorry, yeah, see, there's no light. It's defective.
working?
It's defective.
My God.
This is not what this is working. Okay,
use
use the cube.
Just leave,
Just leave the cube here.
Oh, okay.
You can turn
Sorry.
the sound off.
The
Just
sound?
like that.
Okay. No, I don't have the sound. I have to. No, now I'm listening. I have to mute me. Okay.
Okay, now this works? Yes.
Yeah, but it is linked to the Zoom or not?
Yeah. It's supposed to be linked to the Zoom.
Okay. Okay, so for instance, we know which is the phase diagram of this model in certain. What's something.
Please
Okay.
hold the pause.
Okay. And there's different regions of the phase diagram. We know, for instance, we know that the training it goes from a paramagnetic phase to certain kinds of complex paramagnetic phases. We know, for instance, what happens at the beginning of the learning. We know how features are included in the model, at least at the beginning. We know that the matrix, the coupling matrix starts to encode the principal components of the data set, and that it does this progressively. It first learns the most important direction, and later the second, and so on. And we also have approximative methods to compute the free energy. For instance, we have tap equations to compute the minima of the free energy. So we have a direct way of approximating where the maxima of the probability distributions are. Okay, this is just a sketch in which I projected data on two directions. But normally we have high dimensional data, but we have a way of finding which is the nearest minimum, the nearest minimum in the free energy of a given data. For instance, we can use this to cluster data. We can get our entries of the data and to try to see in which basin of attraction they are, so that we can say which data are similar and which data are very far away. And in particular, since we know that, for instance, during the training, the machine learns in an iterative way more and more important features of the data, we can use this to do hierarchical clustering to see not only which one are very similar, but also which one are more similar than others. And in fact, with this, we can do trees and order the data. For instance, here I show you the tree that we built with the restricted order machine. Okay, this was done by a student, Lorenzo Rosset, in which we generate data artificially with an evolutionary process that has several families during evolution. And when we feed our machine with just the last part of the data, we can see that the machine can really infer all the families that were there just by looking at the maxima of the probability distribution that we have learned. Okay, we can do it also with real data. For instance, here I do it with a NIST, and we can see that just analyzing the machine that we have learned, the machine has learned to distinguish the different numbers by alone. Here I'm not giving any kind of label. Okay, this is not particularly useful. I mean, we have methods to do classification quite better, but it's quite useful, for instance, in proteins in which we have many sequences, but we don't know the function of most of them. Okay, with this, we can do trees of data, and the most reasonable choice, the most reasonable guess is that, okay, here the layers outside are sequences for which we have an experiment that tell us which function it is. These are enzymes. So we would say, okay, all the sequences that enter in a given branch, the most reasonable assumption is that they are very similar to each other. So we can use it for this kind of application. Okay, I gave different reasons that we like from physics, because we know how to play with these models, but also they are quite good because since they are quite simple, they can be trained with not too many data, which is the typical situation in the data sets in biology, for instance. And also it has but they work quite well when we don't have a translational symmetry to deal it. For instance, with sequences, restricted Boltzmann machines perform really well. Okay, this was, I was discussing mostly the easy model, the restricted Boltzmann machine, but okay, in the machine learning literature, we have all the very complex neural networks that we can train, okay, for instance, the generative convolutional networks. From now on, all the rest that I would say, it really applies to all of them. I mean, the facts of the Monte Carlo sampling, it doesn't really matter which is the energy function that we consider. It happens exactly the same in the easy model than in a complex network. Yeah?
How do you choose the number of people?
I don't know. I think, yes, they check and that it works well. And I don't know. I mean, I will show some data that we have done it with a generative convolutional network, but we just took a network that worked from another work and use it to this. No idea. I mean, what we can see from here, I mean, I was arguing before that just by adding a layer of hidden units, we managed to code the correlations between data. Namely, we can understand that the more layers that we put, the more correlations we are able to encode somehow. But, okay, so as I was trying to convince you, I think we can use, in particular, the restricted Boltzmann machine for interpretability applications, because we have an effective model, a physical effective model that we can analyze. So they are very interesting in this point of view. This is a big problem, but it has a big problem, is that these kind of networks are known to be very hard to train. Why? Because one can see anyone that has tried to train this kind of network, not only the restricted, you can see that it's very unstable. Sometimes the training goes well, sometimes it doesn't, and you don't really know why. And you have a very weird behavior in the sampling when you try to generate samples, because at certain times it might be well, you might generate good samples, and another ones you just generate very biased images, and that's what we were trying to illustrate. Okay, here I illustrate you what happens when the training goes bad. Okay, you know what happened. Okay, we did it with the restricted Boltzmann machine. Okay, we have a trained network and we start to do sampling. Okay, we can generate images or numbers. Okay, now we started maybe. But the point is that at a certain moment we can see that the images that we are generating are weird. Okay, this would be real face. I mean, they start to get very biased. If we look to the numbers, we start to generate a lot of ones. I mean, in principle, it was trained with a data set that had all the different digits in the same proportion, and my machine just wants to generate ones and almost the same one. Okay, so what's going on here? Okay, it can be, well, now we are completely sure, these effects are all related to uncontrolled Monte Carlo samplings used for the training. That's what makes these models hard to use or tricky to adjust the parameters. So I passed to discuss how the training is done. It has been discussed several times today. So, but in any case, as I said, we want to make as close as possible our Boltzmann distribution to the empirical one. So one can try to minimize the Kuppel-Leiber divergence, and quite easily we see that we have a term that just depends on the data distribution that we cannot optimize. And we have another term that depends on the parameters, which is the log likelihood. So what we normally do is just to maximize the log likelihood. Okay, so what we want to do is to maximize this object, which is the probability of observing the different entries of our data set, and we want to make them as possible, as high, well, the probability as high as possible. We want them to make the typical configurations of the data set. Okay, what we can do is to do gradient ascent and update the parameters in the direction of this gradient. Okay, so as I said, normally we are gonna have models that have visible and latent variables. The visible will be the data. That is the one that we want to adjust. And we have the hidden. So we are not interested in the probability of the energy of the network, but on the marginal one, as I already said. Okay, so the energy I'm referring here is the energy of the data. From now on, I'm not this. Everything will be just formulated in terms of this energy, not the model one. Okay, so the log likelihood is the average of the logarithm of this probability distribution on the data, and this has two terms, minus the energy and the partition function. And it's clear now that here we have a problem. We cannot compute the log likelihood because we cannot compute the partition function. Okay, for the gradient, still we can derive, and we're gonna get two parts. One in which we have the gradient of the energy averaged on the data, which is easy to compute, and we have this other term that it's averaged on the model. And this is when we are gonna have the problems of the sampling because we need to be able to compute these expectation values. Okay, from the moment I don't imagine we are able to compute properly the gradient. Just if we look at the gradient update dynamics, okay, we are going to compute this gradient, we update the parameters, so we would mow up. I mean, this does not need to be convex, but we should in the training when this gradient, if it happens, vanish, if it ever stops, but okay, we have a fixed point or several fixed points of the dynamics where the gradient becomes zero. This tells us that at the fixed point, we have that the gradient of the energy averaged of the data, it has to be equal to the gradient of the energy averaged on the model. So this tells us what the machine is actually doing. I mean, we are trying to match these two kind of moments, which is just the gradient of the energy. Okay, before I was illustrating this on the opposite way around with the easy model. So in the easy model, okay, this problem is compact. We just have one solution, and if we do exactly the same, it will be deriving the energy with respect to the different couplings, or the different parameters. Okay, we would get that the correlation, the two-body correlations have to be the same in the data and in the model, and same with the frequency. Yeah.
Obvious reason why you need to have the collective at the level each theta I.
Well, because we are computing the gradient with respect to each of the parameters.
Okay, no, yeah.
Okay, this here I'm assuming that we get to a fixed point. I mean, it might be that we don't,
Yeah.
but at least we are trying to optimize the parameters so that these two expected values match, the two moments match during the training. So, okay, for the easy model it's easier. For more complicated models, it will be more complicated connections, and the more parameters that we have, the more conditions we are introducing in the fit. Okay, so if we have trained properly, okay, we have found a good energy function, and our energy function has to fulfill this when we average it on the data. So we expect that if we now sample the configurations of this energy model, okay, it would take us, if we start at random, it would take us some time to thermalize, and at a certain moment we will start to visit the typical configurations of the equilibrium configurations of our model, and if we sample more, we will visit more and more configurations. That's what we normally are used to. Okay, so this is the case in which things work properly. So we stay there and we visit the equilibrium configurations. This I already saw it. Okay, but as I saw but before in the example that I put before, this is not what happened because, okay, at a certain moment we generate good samples, but at a certain moment we start to generate something that doesn't look well, no? So what was wrong, it was precisely the calculation of the gradient that I was saying before. Okay, so as I said, we have an easy thing and a hard thing that we need to do sampling to determine it. Okay, so we know that using Markov chain Monte Carlo, we can always generate samples with a desired probability. So if we wait long enough, we should have a set of independent samples, and we can use it to compute averages in the model. The problem is that we know that we have to wait some time, and some time it has to be longer than the thermalization time. The problem that we have normally when training these kind of models is that we need to do this sampling every time that we want to compute the gradient. So typically, I don't know, we do 10 to the 5 or 10 to the 6 updates. So we cannot do an incredibly large sampling every time because it's just too long. You cannot do it. So you know that you're not doing well, but you can. So the standard approach that has been over the literature in the last years, now they are coming with other solutions, it's okay, we try to parallelize as much as possible. This is quite well with the restricted, but on machine you can update all the spins in one layer and on the other one at the same time. We just do some few steps, and what we try is to choose good initialization to the chain. So, okay, we don't thermalize, but we are nearby the equilibrium. Okay, so there was, in fact, these methods were popularized by Quinton when he proposed the contrastive divergence. So the idea is, since we want to describe the data, the entries of our data set, we can initialize the change every time on an entry of the data set, just do some few steps. He was proposing one, so, and just use it as a good approximation. Okay, it was a much better refinement of this idea that is saying, okay, since we are repeating the sampling process many times, let's keep the last configurations that we had from the previous sampling and use it for the next one, because we are changing the model very slowly. So if we have thermalized in the previous update, we should continue, which is the reasonable thing to do if you want to try to keep equilibrium. Okay, there were other solutions proposed by Marilu, that, okay, you can use the fixed points. As I said before, we can compute where the minimum of the free energy of these models are, for instance, with the restricted Probab machine. So we can use them to compute the mean values, and you can train like this. There have been approaches to try to use parallel tempering. We had just like umbrella sampling methods that, as I said, Aurelian will discuss about this to try to do the sampling better, but I won't discuss anything of this here. And okay, we proposed, and we discovered later that we had been proposing generative neural network before to try to do full, because we wanted to understand what was the effect, to do full out of equilibrium. Let's start every time at random. We just do some steps and see what's happening. Okay, at least when I started to try to use this in practice, I was very frustrated. I said, but okay, I choose a number of steps, but this is good approximation. It is bad. It's extremely hard to find papers in which they try to compute the mixing time or how the mixing time changed during training and all this. So we did a bit what we tried to do in physics. Let's do an experiment. So I have to do sampling. So I can do a training in which I control that I always do enough steps to thermalize. So I know that I'm computing well the gradient, or I just fix a number of steps. Starting from random. In both cases, we were starting from random to be sure that to check well if we were thermalizing or not. And okay, let's do just some few steps and use it like this. And the results that were, we have quite a lot of experimental results there, they were super clear. In the case we were computing the gradients as we should, we were getting stable models that did what we were expecting, that the equilibrium configurations of this model, they were very similar to those of the data set. In the case we were doing this, what we were getting, it was very weird models with memory effects in which we could recover the data, we could generate good data, but only if we sample the model in the same way that we had used during done during the training, which seems a bit reasonable. In one case, we teach the machine to learn the Gibbs-Bowman, to adjust the Gibbs-Bowman distribution. In the other case, we are teaching the machine to dynamically generate samples in a given number of steps. So let me, because this event it can be understood very, very easily. Now we know. Okay, so as I was saying, we have to do a sampling every time we want to compute the gradient, to compute this gradient of the energy. Okay, when we are doing a final time sampling, we are not using the Boltzmann distribution. We are computing with a dynamical distribution that we actually know quite well who it is, because this is a Markov process. So we know that this distribution, I mean, if we had a vector with the probability of all the states in our model, this is going to be a probability that it's going to depend on the initial distribution that we choose. The stochastic matrix up to the number of steps. The stochastic matrix, we know it. So this can be integrated. We know which distribution we are using to sample the states. We cannot compute it, but we know who it is. And it depends, okay, it will depend, okay, the largest one, it will be the mixing time. Okay, so according to the discussion that I was saying before, we have a dynamics that does not have the fixed point that we wanted. Okay, no, indeed, this actually wrong. Okay, this does not have the fixed point, this one, but now we are using another gradient, okay, which is the average on the data minus this average on the dynamical distribution. Okay, so the fixed point is not going to be the one that we wanted to have. It's going to be this one. Okay, we are fitting the data, we are fitting the parameter so that the set of equations that we have to fulfill to end the training are equal, averaged on the data set and with this dynamical distribution. Okay, before we had it with the Boltzmann one. Okay, so this means, of course, that there is no reason why these two things should be connected at all, but we know that we can recover the data. We just need to repeat being able to generate data with this distribution, which we can, because it's a Markov process and we can repeat it. I don't know. Okay. Let me illustrate what I mean by this. Okay. For instance, imagine that every time that I do the training, I initialize on random and just do 100 steps. Okay, so I repeat the training many times. Okay, I end up with a model that if I initialize my Markov chains at random and I do sample, okay, here we have 118, but okay, we do essentially 100 steps, we recover the data set with the right diversity that what we were expecting. But now if I continue my sampling for a long time, I start to get just once. Okay, this is growing exponentially. And we have something that it was very different to the figure I saw before, because this model is extremely slow. Okay, this is completely frozen. Numbers are not changing anymore. What happens now if I change the initialization? For instance, imagine that I used contrastive divergence for the training, so that every time I was initializing at the data set, if I take this machine and now I try to sample from random, I never get any kind of number. And these machines are quite weird, because if you look at the log likelihood, they are extremely good, but they cannot generate that because I changed the initialization. You can play quite a lot. Okay, this was the same. So if I now, for instance, okay, this is the same, but it will happen the same. If I change the initialization in the one I train from random, you don't get it. Or for instance, you can change the dynamics you use to train the model. For instance, if we train a machine using the TAP equations, as I said, the minimum of the free energy, and now we take this model and we try to sample from random, you don't even get numbers either. You do get numbers if I sample using the same sampling strategy that I did during the training. Okay, this in fact, it had been proposed in the last year as a very efficient way of generating high quality high quality samples to initiate the Markov chains from random and just doing some few steps. Okay? And it has been done with different cognate. Okay, all these fixed point that we got here, you can actually show that this is a theorem, it has to happen, and all the consequences that I'm gonna show later. If we assume that the fixed point is reached, which might be not the case, all the rest of the things can be proven. And also it can be proved that we don't really need to be at the fixed point, we need to be nearby the fixed point to prove it. Okay, so the first consequence is that, okay, if we have done equilibrium, we would be matching these moments, okay? If we do non-equilibrium, we are matching these moments, but the quality of the samples that we can generate is exactly the same because the conditions we are going to follow are the same, at least if we look at these observables. Of course, if we did equilibrium and we learned the right moment, other observables, they might be better, but the conditions of my training are gonna be the same. So I expect that doing this out of equilibrium procedure, I should generate as well as if I did the equilibrium one, okay? And in fact, it's something that we have seen at least in the first paper in practical, and we know that quite a lot that if we want to generate good quality images, the best thing that we can do is to go full out of equilibrium, not trying to thermalize, because we cannot thermalize, so just do it in that way and we get, okay, in this case it was also with 100 with different data set, we can generate high quality samples. This is that with an RBM, which is not very well suited for images, and still it does it quite well. Yeah.
Description to choose the time.
Now I go. It's with the consequences I'm saying. Okay, the next thing that we see is that the quality of the samples that we can generate, they cannot depend on K. They cannot depend on the initialization, and they cannot depend on the dynamical rules that we use. As long as we don't thermalize, doesn't really matter, which is extremely anti-intuitive, but I mean, experimentally, we can see that this is the case. For instance, if we do inverse problem, okay, we generate samples, equilibrium samples of an easy model, so we know which are the true couplings. Okay, we can try to learn the couplings using maximum likelihood training, exactly the same. And we use for the non-convergent Monte Carlo samplings, okay, we have to match that the statistics of the frequencies, they have to be the same dynamically, and the same for the frequency and the same for the covariance matrix. Okay, here I saw the error we do in the covariance matrix. Okay, we compare the covariance matrix of the generated samples and the covariance matrix of the original ones. Okay, so, and this is in log scale, so the lower it is, the more similar they are. Okay, the different colors is different training epochs. So the blue one is the most trained machine. Okay, this is a model that we train just initializing at random and doing 5 Monte Carlo steps, and you can see that we get a very clear peak of good quality samples at the right K when we resample. But one of the very impressive things is if now we repeat the training for using different values of different number of steps during the training, for instance, using 1, so we just initialize at random, we do 1 step, we use this to compute the gradient, we get exactly the same quality. I mean, we don't show it here because you don't see anything. I mean, you see a peak that starts at 1. So you can get, in principle, the same quality doing with any K. Okay, what I said. Okay, this kind of, okay, this is numerical, but we can describe this analytically, for instance, in the Gaussian model, or it can be described this model at high temperatures, and we can describe this, the quality in time, and you can see that it has to be like this. Okay, we could do this with a restricted Boltzmann machine. These are machine trained from random with 10 steps, 100, 1,000, and 10,000. And you see that the best quality is going to arrive at the same sampling time. And also that the best quality that we get, it does not depend on K. So there's no point of doing this if you just want to generate. Okay, this can be done with a generative concept, and we get exactly the same here. The quality is measured with the Fletcher Institute score. So this is clear. In our matching, it does not depend on the energy function. So in principle, any energy function that we choose, it has to fulfill this. What's the nice thing is that, okay, we can use this kind of approach to generate highly structured data. For instance, if we have multimodal data, like for instance, okay, here I have this genome data, protein family, and RNA family, that, okay, these have been projected on the principal component. You can see that they have really well separated peaks. We can generate high quality samples. In this case, we even generate constrained to having one particular characteristic, just with 10 steps. We have a direct way of generating very fast samples, which even if we had trained the models perfectly, it would be almost impossible because, I mean, the time it would take you to jump from the different peaks, it would be forever. So even if you have a good machine, you cannot generate because it takes you for a long time. One can see, I don't know, the ones that you know, this is very similar procedure that what happens with diffusion, which you train the model to decode the data from random. That's what we are doing. We are training the model to, starting from random, in 10 steps, for instance, generate data. And we can train it to do other things. For instance, in the work I was discussing before, we can teach it to generate, I mean, if I give it a label, I can teach it to generate the right kind of samples given the label, for instance. And okay, so just in summary, okay, if we want to generate samples, I mean, if we want to use this model as generative models, there is absolutely no point of trying to thermalize because it will be very costly to train and it will be very costly to generate. So it's better to go with this out of equilibrium strategy, which is always very stable. I mean, it's really hard to make a training that doesn't work. If you do out of equilibrium, it always works. If you try to do equilibrium, it's tricky. I mean, because it depends if you really equilibrate it well. But I was saying at the beginning of my talk that what I wanted was to get an effective model for my data. So in principle, there is no reason why these models that I'm getting like this, they are good models for my data. And in fact, they are not. Okay, I was showing before the inverse Ising case in which, okay, we generate data with a given coupling matrix. So we can compare the coupling matrix that we infer with the one that we had originally. And what we see here, okay, this is done with K1, the one that we just do one step, I was saying before. Okay, with this machine, which is the oldest one, we can generate data very well, very high quality data, but we get a horrible coupling matrix. It has nothing to do with the original model that I had. Okay, we can use, for instance, the method I was discussing before, in which we can make a mapping between the RBM that we have learned and the effective model of this RBM in the generalized DC model. Here, I train the machine with 2D Ising samples in equilibrium. I train the machine using the out of equilibrium study. I think it was with 10 steps. And we see that we reconstruct a machine that it has a model that it has a lot more interaction than what it should. In particular, it seems to have like next to neural network, next to nearest network, neighbors couplings. And for instance, if I try to do this clustering that I was saying before, just by looking at the minimum of the probability distribution, normally the trees that we get, if we try to do it with MDs, if we try to do it, they don't perform well. So for interpretability, we cannot use it, but you can use it to generate. Okay, so as I said, in principle, I was interested in the problem of modeling, so this is useless for modeling. It's good for generation. If we want to equilibrate, Aurelian will be discussing of the kind of things that we try to do to compute this better. And okay, with this I finish. I thank my my group in Madrid and a group here in the Paris Saclay, and Elizabeth, who worked with us in the analytical description of the training. Okay, so here you have the papers, and normally all the codes for the numerical works are in GitHub. And thank you very much. Okay.